Okay, everybody, we're going to be starting off today working on part one of theorems with circles. Again, we've talked a lot about circles already this year, talking about the lengths of arcs as well as the area of pieces of circles, as well as, of course, reviewing things like circumference and area. We're now going to be taking it to a new level where we look at specifically things that go along with circles, as well as some formulas that come out of that. It is going to be important that you have a general understanding of these. However, usually on tests, I'll let you guys make sort of a theorem checklist that you can look at, because I don't believe in memorizing everything. But I want you to understand. The main goal here is to understand what we're doing. Okay, so here's the first page of notes you're going to do. Some of the activities that normally we would do will be done in class. So because of that, I will be skipping over some things a little quicker. However, I'll still be explaining the actual theorems themselves. But some of the activities we're going to do to understand the theorems, those would be things that were already done on your notes. But this is the page we're talking about now. Okay, so starting out, you already have these things labeled on your notes, but we're going to look at one piece at a time. What my goal for you guys to do is to define these in your own words. So first we have a diameter. Okay, as you know from class time, that would be defined most likely as a line that cuts through the center of the circle, cutting it into two equal halves. We have a radius, which cuts halfway across a circle, directly to the center. That's important. We have a chord, which connects any 2 points on the circle. A diameter is actually a special kind of chord that also goes through the center. We have a secant line, which is a line that's basically a chord that continues, if you look at it that way, but it's a line that crosses 2 points on the circle. And we have a line that crosses only 1 point on a circle, which is called a tangent. In addition to that, it's not going to show in your notes, so you may want to kind of shade it a little bit if you don't already have it, but an arc is a piece of a circle. So this right here is considered a minor arc because it's less than 180 degrees. A major arc is more than 180 degrees. So as you can see, it goes just past the diameter. So that's called a major arc. So if you haven't already done it, make sure in your notes that you update all of those things. Okay, the next thing we're going to do, this is an activity we did in class. So if you're doing the notes for the first time, you're going to want to do this on your own and pause the video. But we're going to take any point on the circle and draw the tangent line through that point. So you would take a ruler and you would draw any random tangent line. I put one right here, but the whole point is to try a bunch of different places. Okay, next what we're going to do is we're going to connect this point to the center of the circle. And what I want you guys to do is go ahead and see if you notice anything. So on your example, pause it, take a look for a second, see if you think you know anything special about that angle. What you should have noticed is that actually makes a 90-degree angle. So what the theorem says is that any line is tangent to a circle if and only if the line is perpendicular from the center of the circle to that point. This is a book definition, but one of the things I wanted to highlight with you guys is the if and only if part. Kind of give you an idea what that means in geometry and sort of in proof in general. If and only if means it works both ways. It means if we have a tangent line, okay, and it connects secondly to the center, a line connected to the center, then it must be 90 degrees. Secondly, what it's saying is if I have a radius and it makes a 90-degree angle, so first I have the radius, and secondly it makes a 90-degree angle with a line, that line must be a tangent line. Okay, now we're going to be moving on to the second page of our notes. And again, you should have copied down that theorem, so if you didn't already have it in your notes, you're going to want to go back and take a look at it. We're going to now do a couple practice problems. So looking at the first one here, the reason that we mainly use it, because obviously when you look at something you say, oh, that's 90, that's, it's interesting to know that, but it doesn't really do much for us in terms of problems. What we need to be able to do is we need to be able to go ahead and set that up into an equation and into a problem. So usually what 90 degrees tells us is right triangles. We know SOHCAHTOA, and we also know how to do Pythagorean theorem from that. In this case, I say, hey, wait a second, because it's a tangent segment, because it's a radius, therefore it's 90 degrees. Now I can apply Pythagorean theorem. Pythagorean theorem is r squared plus 16 squared equals 20 squared, because remember, in Pythagorean theorem, it's leg squared, hypotenuse squared. So since r squared then is equal to 144, remember I got that by taking 400, which is 20 times 20, and subtracting 16 times 16, which is 256, which then gives me 144. I then take the square root, which gives me 12. Looking at our second example, again, you can see we're going to have to notice, hey, wait a second, if that's a tangent line, therefore it's a right triangle. When it's a right triangle, I can go from there. That x does not represent the whole part. The x represents only the outside. So from here, we're going to go 6 squared plus 8 squared equals x plus 6 squared. What that requires you to notice, and this is one that people get stuck on, is that if that is also the radius right there, then that's also 6. This is a problem, the kind of thing that you'll see on a test, and that a lot of people get confused on. They don't realize that any line, any straight line connecting from the center would also have to be 6. That's a fact that's important for a lot of examples we'll come up with. There's only so many pieces of information you know. Okay, now we're just going to go ahead and simplify it. 6 squared is 36, 8 squared is 64, that makes 100. A lot of times people would think, oh, I have to go ahead and do Pythagorean theorem, I have to do quadratic formula, multiply stuff out, do all these things. You don't have to do that. If we went ahead and multiplied x plus 6 times x plus 6 from algebra, as you remember, you would get x squared, which means you would get 2 answers. However, we're not going to get 2 answers on a problem like this, simply because on a problem like this, we don't have negative values. We're not going to end up with a negative value of x. Okay, so from there, we're going to take the square root of both sides, which is going to give me 10. Square root of 100 is 10. And when you take the square root of something squared, the square symbol just goes away. Okay, from there, I'm going to subtract 6 from both sides, and I get x equals 4. On both of these problems, I know I should have done this earlier, I'm being mean, but they were also both 3, 4, 5 right triangles. So if you remember back to what we did earlier in the year, you would have noticed that 6 is 2 times 3, 8 is 2 times 4, so that would mean the hypotenuse would have to be 2 times 5, which is 10. You can see where that comes into play in the problem, 10 equals x plus 6. So then that would have to be 4 left over. And the top one, of course, was a 3, 4, 5. 4 times 3 is 12, 4 times 4 is 16, and 4 times 5 is 20. Okay, the next thing we're going to look at is we're going to pick a point anywhere on the outside of the circle, and we're going to draw 2 tangent lines from there. There should only be 2 tangent lines that occur based on whatever point you pick. I want you to pick your own point, don't pick mine, and we're going to try to discover another theorem here. You're going to need a ruler for this as well. After you do that, what I want you to do is measure the 2 segments. Okay, so what you should have noticed, hopefully, is that the segments are equal to the same length. And that is true of any point you picked. So hopefully you picked a point different than mine. If you want to test it again, just pick another point on the other side of it, closer than the circle or whatever. You're going to notice that that's always true. Now, it's hard to draw a perfect tangent line, but that is, in fact, the rule if you draw the tangent line that hits exactly one point. So here we go. The theorem states tangent segments from a common point outside the circle are always congruent. So let's kind of make some sense of that. We're talking about tangent segments. Okay, so by that we mean the 2 purple segments that connect at one point each, right there and right there, from a common point. So that common point would be right there, the point P, outside the circle. So the point can't be in the center, the point has to be outside the circle. Obviously, if we take a point inside the circle, those are not going to necessarily be equal to each other. It's kind of obvious. But outside the circle and including tangent points, it's always the same. Okay, it's a very simple idea, but it does lead to some practice problems. So let's take a look. Alright, so here's a practice problem for you. You may have to fill in the 3x plus 10 and 7x minus 1 on your notes. If not, you're going to go ahead and set it up. So what the theorem says is because they are both tangent segments and because they're from a common point, therefore we just set them equal to each other. Okay, so all you're doing is you're solving a equation with variables on both sides. We'd subtract 3x from both sides, add 6, and divide by 4, and we get x equals 4. If I then asked you to figure out exactly what the segment was, you would just take that 4 and plug it into one of them. 3 times 4 plus 10, and you would figure out that that's going to be, each one is going to be 22. Okay, now we're moving on to the next page of our notes. As you can see, this is page 3, so make sure you have that page available. Okay, so we're going to start with the central angle and define it. So A definition of a central angle is an angle made from the center and 2 points in the circumference. Anytime we have an angle, we have 3 points to create it. So what it's saying is one of the points, the vertex, is always going to be in the center, and the other 2 points will be on the angle, on the circle itself. And that's called a central angle. It's an easy way to remember it, comes from the center. Okay, an inscribed angle is the next one we're going to talk about. An inscribed angle, all 3 points are on the circumference of the circle. So if we pick any 3 points in the circle and we connect them, that creates an inscribed angle. These definitions will be important as we go forward, very important, so make sure you know them. Okay, when we talk about the measure of an arc, we know about angles. Angles are measured in degrees. Well, we can also measure an arc in degrees. So for example, if I take a look at AC right there and I say, hey, that piece right there, that piece that I just highlighted in red, what's the measure of that arc? Well, in order to do that, we need to know the measure of the central angle. So if I take a look from the center and I say, hey, that's 60 degrees, that means then that the arc is 60 degrees as well. So first of all, here's my question. When I say AC, how do I know that I mean that arc and not the giant arc that goes around the other side of the circle? So obviously there has to be some way to do it. The way we do it is we go ahead and throw a third letter on the circle. Now, if I want to talk about the large arc, which has to be 300 because the full circle is 360, then I would use something such as ABC, or I could also use CBA. ACB would be different. That would be including the red one plus a little bit of extra. So you want to make sure that you're always using the right terminology. But basically what we do is when we talk about minor arcs, we use 2 letters. When we talk about major arcs, we use 3 letters. You may even see 3 letters for a minor arc, but in general that's the method. And that right there in purple is the major arc ABC. Okay, so the next thing we're going to do is we're going to compare inscribed angles and central angles. So what we're going to do is create a central angle. And we're going to say which is going to be bigger. If I take that same angle and I move it back to here, that's the same angle copied over, and then I just simply extend it out until it hits the circle. As you can see, that inscribed angle makes a bigger arc. The question is how much bigger? Is it, twice as big? Is it 3 times as big? Is it half again as big? 1.5 times? So we're going to need to go through a process and kind of take a look at it. So what we're going to do is the first thing we're going to do is we're going to go ahead and we're going to copy down onto your paper an inscribed angle. So you're going to plot any Y, R, and S on there, like I did, and connect them onto your notes. Any 3 points will be fine. Okay, from that you're then going to connect the center out. So it looks like my shape could be a wider triangle, a narrower triangle. Now what I want you to do is I want you to trace the angle. I only want you to trace the angle right here. Okay, I want you to notice that angle right there onto some tracing paper. If you don't have tracing paper at home, simple, computer paper works, or even lined paper. So you're going to trace that one, and then you're going to copy it down and compare it down to the angle below. So take a second and trace that, and then see how much of the big angle, the central angle, it fills up. What you should see is that perfectly it cuts it in half. So as you can see, 2 of those inscribed angles is perfect for the central angle. So really what this is our way of kind of investigating a theorem. The theorem says that an inscribed angle is always half as big as a central angle, or another way of looking at it, the central angle is twice as big as the inscribed. So we're going to write our formula now. And it's just exactly what we said. If we take a central angle and an inscribed angle, so that if that angle's beta, then the central angle would be twice as big. It doesn't matter how you draw it. The central angle would be twice as big. Okay, so that means that any inscribed angle as well works. So for example, if I go ahead and I draw one that connects here to here, that is also half as big. Okay, any inscribed angle. And we're going to look at a theorem about that in a second as well. Okay, so as it says, half of the large angle XCZ is equal to XYZ. Or as we said, if you take double the small one, you'll get the big one. So let's take a look at some actual practice. So we're going to go ahead now to page 4 of our notes. And you may need to fill in a couple pieces on there. So what we're trying to do here is we're trying to find the value of x. What we know is that the central angle is x on there, and the inscribed angle is 18. So even though it's not one right on top of the other one, we will be doubling the inscribed angle to get the central angle. Looking at our second example, go ahead and pause it if you need to. Alright, so this time we have the central angle. Remember, the central angle is twice as big as the smaller angle. So what that means is we're going to end up with 142 divided by 2, which is 71. What I would hope you guys would do here, even though we say not to look just at the angle as a reference, obviously that angle x on the bottom one is smaller than 142. The only mistake I would see you making would be to accidentally double it. So instead of cutting it in half, you might say, oh, it's 284. I want you to think if that makes sense. Does that angle look like a 284 degree angle? Use your common sense and make it work for you instead of against you. Okay, the next thing we're going to do is we're going to go ahead and look at what happens if we have two inscribed angles that take the same points. So if I connect, basically what I want you to do is I want you to pick any points x and z on the bottom half of the circle. You could literally pick them anywhere, but if you end up making a diameter or something, it's just going to confuse you. So pick any 2 points and try to keep them both in the bottom half of the circle, but pick different ones than I did. Now pick any point on top y. You're going to connect those. Okay, now you're going to pick another point, w, anywhere on top as well, and you're going to connect that as well. What I want you to do is I want you to go ahead and trace one of them. Trace x, y, z, the one that I have in yellow. Trace the first one, but it doesn't really matter. You're going to trace either angle, and you're going to compare it to the other one. Just take a second to do that. Hopefully what you noticed here is that, simply put, this is another theorem, any inscribed angles that inscribe the same arc are equal. Meaning, looking at the 2 points that make our arc, okay, we have our arc right here, okay, our arc. Any angle that I draw that inscribes those will be equal, meaning I can go anywhere on the circle that I would like, anywhere. All of these angles should be, as long as I did my lines correctly, and I did them very quickly, but all of those angles are equal. And you can kind of look and see that. It's very interesting, especially as you get over on the side here and you're thinking, man, how could that possibly be? It's so much wider. Well, no, it's not really. Okay, anywhere you go, even though it seems like you're going to make one of them really, really wide, well, the other one has to be very narrow to make it work. So as you can see from this picture, they're always the same. And here's why, just a really quick proof. Well, they both have the same central angle, so that means that xyz is doubled to equal xcz. The same thing is true for the other one. Double xwz must also be xcz. Well, you set them equal to each other, divide by 2, and you've got that they're equal to each other. So it's a very easy proof, and it seems like we can prove it sort of just by looking at it as well. But it might not be something you would have expected. Okay, so we're going to move to the next page of our notes now. We're going to talk about a couple more theorems. Okay, the first one is called the inscribed angle on a diameter theorem. So what I want you guys to do is on your paper, you have the line that's drawn horizontally. I want you guys to go ahead and pick, and your paper should look like this. I want you to pick any point anywhere on the circle that's not already x or z. It needs to be a new point, but any point, and call that point y. Here's where I put mine, but call any point you want and call it y. And then connect the triangle. We know that it's an inscribed angle, but I want you to go ahead and take a look at that angle and see what you notice. Okay, what you should have noticed is that it's a 90-degree angle. Okay, as you know, the inscribed angle is always half the arc. So if you look at a 180-degree arc, which is half a circle, well, half of 180 degrees is 90 degrees. It makes sense, but it's kind of interesting how you could put a point absolutely anywhere on the circle, and if you connect it to a diameter in a triangle, it makes a right triangle. So thinking about some of the examples you could use, now you've got right triangles, you could use SOHCAHTOA, Pythagorean theorem, all those things will come into play. Okay, so let's take a look at the theorem. The theorem says, a triangle inscribed in a circle is a right triangle if and only if one side of the triangle is the diameter. Okay, what that means is, if you take a diameter and you inscribe it, you get a right triangle. Conversely, if you have a right triangle and all 3 points are on the circle, the hypotenuse must be the diameter. So that's kind of you can go either way with it, as we've said before with if and only if proofs. Okay, so the next theorem we're going to look at is about quadrilaterals inscribed in a circle. Remember, inscribed means all the points are on the circle. So we're going to pick 4 points, Q, R, S, and T. The only thing I want to make sure you do is I want to make sure you go in order. So it should go like, if you're looking at the mouse, Q, then R, then S, then T. So in a circle, it goes Q, R, S, T clockwise. These are the 4 I picked. Just pick any 4 random ones. But it is important that if you look at it and we connect it like we're going to do, that T and Q are across from each other and S and R, only for what we're going to look at in a second. So pause it, pick any 4 random ones. Please pick different ones than me. Pick any 4 random ones, and we'll go from there. You're also going to need a protractor, so if you don't have your protractor with you, when you pause it, go grab your protractor. Alright, so what I want you to do specifically is take your protractor and measure these angles. First, look at Q and T and see how they compare to each other. Then look at S and R and see how they compare to each other. We're trying to find a rule and a pattern that can help us in these problems later on. So take a few minutes to do that, pause it while you do so, and then hit play when you're done. Alright, so what you should have noticed is that the angles across from each other add up to 180. So what the theorem says is, if a quadrilateral is inscribed in a circle, then opposite angles are supplementary. Okay, meaning Q plus T, since these are opposite from each other, shoot a line straight out, you hit T, etc. Those are add up to 180, as well as S and R add up to 180. Notice this proof is not an if and only if proof, because just having 2 angles that add up to 180 does not guarantee you have a quadrilateral. So it's an example of a non-if and only if proof. Okay, so that's the end of the first part of our circle theorems lessons. Hopefully you guys can use this to review the things we've done in class, as well as make sure you understand these theorems.